Hello and welcome to Tonight at 8 from the RSGB. Printed circuit boards, or PCBs, have been around for a very long time, but still form the basis of mounting and connecting components together in even the most modern equipment. Originally mastered using rub-down transfers and tape, they are now designed on computer so that with just a click of a mouse, a design can be printed out and etched at home, or more recently emailed to a PCB manufacturer who can make them in small quantities at affordable prices for hobbyists. Well, our guest this evening is Mike Willis, G0MJW, who uses the free KiCAD software to create quite sophisticated designs, and tonight will show us how to get started with a simple project. Welcome to Tonight at 8, Mike. Can you give us a brief overview of what you'll be going to cover tonight?
Yeah, thank you, David. Well, the plan is to start out from just a simple schematic and go right through how to use KiCAD to put that into a schematic capture and then make a PCB out of it, and then hopefully produce the Gerber files, which you then send off to the PCB house for manufacture.
Wonderful. Well, we look forward to it. And as ever, if you're watching this live, it's on Monday the 13th of May. It is live, and you can ask Mike questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So now let's find out more about designing a PCB with KiCAD and Mike. Over to you, Mike.
Thank you, David. Could you go to the next slide? So firstly, this is what we're going to do. We're going to use KiCAD. That's the KiCAD logo, and you can see actually the final result. So in best Blue Peter fashion, I've done it first, just to make sure all the things are right. Can we go on to the next slide? So this is what the project is. Now, just to be clear, this is not about design. So really the circuit doesn't matter. The point is to actually have a circuit that you can rebuild and place components and do something sensible. So it's really about the design with PCBs rather than the circuit itself. It's a very simple project, and it's using through-hole components. So can we go to the next slide? Now, components. The first thing you need to do when you're contemplating a design is work out what parts you're going to use. And basically, look them up in the catalogue, work out what size their footprint is, how big they are, what type of parts they are, because you'll need that when you come to design the PCB, because the holes and the tracks will have to match where the components' leads are. So in the case of this project, we've got a few resistors, a couple of transistors, capacitor and a connector. Can we go on to the next slide? And this is where you get KiCAD from. It's available for download for Windows, Linux and Mac, and it's free. Donations are welcome. And there's a new version out, version 8. I'm going to be using version 7 in this demonstration because version 8 has only just come out and I haven't downloaded it, but it really won't make any difference which one you download. They are backwards compatible, but not forwards compatible. So if you design something in version 7, you can use it in version 8. If you design it in version 8, you can't go back to version 7. So with that, let's go to the screen share. Now this is what you get when you first load the program. You get this window here, and this is basically the starting point for everything. Now I have a project already loaded, the one that we're going to do. I'm going to redo this, but just to show you the basics first of all of the different parts of the project lie under this main part here, and the first thing you would start with is the schematic, and if I double click on that, you'll see a schematic comes up. That's what we're going to be developing. Now, from that schematic, you develop a PCB. And if I double click on that, hopefully the PCB will come up. So that's where we're going to get to, but I'm going to go through all the details about how to do that from the start. So I'm going to close that down. I'm going to close this project. So we've nothing there. And then I'm going to do a new project. And find a directory to put it. Give it a name. For want of better names, switch to. And there you go. We now have a switch to. And it's all blank. So if I now go to the schematic capture editor, you'll see a blank screen. Nothing in it at all. Now, for the purposes of this demo, I'm going to make a few changes because one of the things that you will see is everything is pretty small. It's very difficult to read on the screen. So I'm going to change the page settings, and instead of it being A4, I'm going to make it A5. Now you won't need to do that if you're doing this on a computer, but I'm going to do it here. And then I'm going to zoom into it because it got smaller. Now hopefully you can see that on the screen, but do say if not. I don't expect you to be able to read the detail of the writing. I just expect you to be able to see the icons and the larger parts in there. But there's a zoom facility. You can use the mouse or you can use these buttons. All the controls are done with the mouse, and I don't think you can see what I'm doing on the desk, but I'm basically using the scroll wheel or the left and right buttons and dragging things with the mouse. So let's make that big. Now, what's the first thing that you want to do with one of these things? Well, there's a box here which has a title in it, and I don't know if you're seeing my mouse or not. I think you are.
It's quite small, Mike, but we can see it.
Yeah, okay. It's huge on my screen, but it seems to come out small via Zoom. So what I'll do is I'll press the E button, and E is for edit. Actually, no, I'll do it with the mouse. I'll right-click. Oops, hang on a second. And I will edit. Why is it not allowing me to edit? Hang on a second. There we go. Wasn't in the right place with the mouse. So this dialog box allows me to say the date, give it a title, company, whatever, revision 1. It's always useful to keep your revisions up to date. And you can see it's now filled in that box. That's the first thing you do, basically. You just set yourself up. Now, the next thing then is to try and draw the schematic. Now, the schematic is actually in the slide deck. I've got a copy of it here. I'm hoping that you'll be able to remember roughly what it looks like, but if you could get that slide up, David, with the schematic and maybe go back to it.
Yeah, sure. Here it is.
There we go. Yeah. So that's what we're trying to create. So we have a MOSFET, a P MOSFET.
That's the top right component, just for those not too into the electronic side, yeah?
Good point, yeah. Q1 is a MOSFET. Q3 is just a normal transistor. Don't ask me why there's no Q2, it's just the design didn't have that in. There's a few resistors and a capacitor and a couple of connectors. So let's actually get around to putting those components in. So if we go back to the screen, if I click on here, we can add a symbol. And what we want is actually the device. And I happen to know, which is why I chose it, this transistor is in the KiCAD library.
So I was just going to ask about this, Mike, because we're trying to make this obviously for complete novices to using software. So when you download KiCAD, which is free, and we'll be telling you, by the way, how to download it later. So in there will be this library of symbols already in there?
Yes, so all the standard components you might want are already included. There's a range of transistors and ICs and various parts. If you don't have those parts, you can quite often download them from the website of the manufacturer or from DigiKey or Mouser, Farnell, RS. They all provide downloadable footprints and symbols these days. And if none of those work, you can make your own. I wasn't going to go into the details of making your own components in this talk because it would take too long. But basically, if it's using fairly standard components, they should be there in the library already. So in this case, this MOSFET, which incidentally is quite a beefy one, it'll work at up to 27 amps and 60 volts. That's in the library, and that is what I'm going to add first of all. The other thing you can see incidentally on here is the footprint that the package has on a PCB.
And again, if you don't mind, Mike, just me mentioning, for those really just getting started to this, we'd call the footprint those 3 pads, as we call them, don't we? They're the 3 bits of copper that will end up on the circuit board to make the connections with those 3 pins from that transistor, yeah?
Yep, that's right, David,
okay.
Yes. So again, you can design the symbol and you can design the footprint. So the footprint is what it looks like on the PCB, and generally there are different layers, which I'll come into when we do the PCB design. I'll explain what the different layers are, because there's copper, but there's also labels and what we call the silk screen, which is the thing that gives you all the component legends and what have you. So let me take that and I'll just place it roughly there. And the one thing about that, now I've placed it and I'm going to zoom in, is if you look at that, it's not really in the right orientation with respect to the schematic. Now, pin 3 is basically where the current is going in, and pin 2 is where it's going out. So I could try and rotate it, and you rotate it simply by pressing the R button on the keyboard, but even so, output and input are the wrong way round from the point of view of this circuit. So you have this is right-clicking the mouse. You can mirror vertically, mirror horizontally, rotate clockwise, rotate anti-clockwise. What we want to do here is we want to mirror horizontally. So now magically, pin 3 is on this side and pin 2 is on that side. Makes your life a lot easier when you're trying to wire things up. So when you look at the symbol on the schematic, try and make sure that what you put on when you put the schematic into KiCAD is the same way around or the right way around. It makes life a lot easier. So that's that particular device. Now the next device I'm going to add are some of the resistors. So again, to do that, to the symbol, I'm going to start typing resistor, and you see here it's come up R, and that's the resistor symbol. But what you notice is there's no footprint for this. So I'm going to explain how you deal with that. So let's put in a resistor, and let's just put it about here for the moment. And then I'm going to edit it again. So I'm going to look at the properties. And you can see here there's a reference, a value, which we can fill in a moment, and a footprint, and there's no footprint there. Now there's a library of footprints in KiCAD. So if I click here, this will open up the library. And this is the library of footprints. Now, what I need to do is find one. So let's do that again. That's the resistor. And sometimes it opens up relatively small, so you can't see it. We've got all the connectors there, all the possible things. If we go down to R, we should see some resistors. So we've got resistor SMD. SMD stands for surface mount. Resistors THT, that stands for through hole, and that's what we're going to use. And from experience, I know that the resistor I want to use is the resistor that has a, well, let me just expand this out so you can see it a bit better. It has a diameter of 2.5 millimeters, a pitch. Now the pitch is the distance between these two holes here of 10.16 millimeters, which is 0.4 of an inch. And it's horizontally mounted on the PCB. So if I double click on that, that will put that in there, and that gives us the resistor. So we now have a resistor R1 with the right footprint. Now the other thing we need to do with this resistor is set a value. Now in this case I'm going to set that value, and I'm going to set that value to 22K, which is what the R1 was in the original schematic. So again, properties, value 22K. Now that doesn't do anything with respect to the program, but it gives you the value which will be useful when you come to build it. And it comes into the bill of materials. Incidentally, to deselect something, you just press the escape button. Now, I could go through that whole process again, or, and this is one of the shortcuts which KiCAD has, I can just duplicate that component. And to duplicate a component, I can either use the mouse and go to duplicate, or I can type Control D. So this time I've done the duplicate, and I'm going to put that there. And actually, I'm going to duplicate it again, so this time with Control D.
So at the moment it's just duplicating the footprint that you decided, because presumably all your resistors are going to be the same size, so this will work for all of them, yeah?
That's right, and I'm going to rotate that one because I know that one needs to go over there in my schematic. And I'm going to grab this one again, and I'm going to duplicate it again. So that's now all the resistors put in without too much effort. But of course the values are wrong, because R2 should be 10K according to the schematic. Maybe we can go back to the schematic briefly, David. You see that?
There we are.
So R2 is 10K, R1 is 22K, R3 is 1K, and R4 is 10K. Now you'll have the schematic next to you rather than on a shared screen, so that'll be easy to work out. So a shortcut again, instead of going through that big dialog, if I just type E here, then a dialog box will pop up and I can just type in 10K. And for R4, which is also 10K, I can just type in 10K. And for R3, which is 1K, I can type in 1K. So that's all the resistors in our schematic. Now we have another transistor, a BC546. So I think you might be able to work out what I'm going to do now. I'm going to click here. I'm going to type in BC546. Lo and behold, BC546. And it has a footprint, so that's fine. I can double click on that. I can move it around, and I notice it's actually the right way around for how I want it to be in the circuit. So I'll put that in the circuit there.
But if it wasn't, you'd be able to rotate it and manipulate it in the same way as you did for the
exactly,
other effect,
yes.
Yeah? Okay.
Yeah, exactly. So again, press escape to deselect. I've got this little arrow thing here now, where I've got the mouse. If I click on this resistor, I can type M if I want to move it, because it's a little bit low. So I'm going to move it up there a bit. And the reason I'm doing that is so that it looks a little prettier. I'm going to move the transistor down a bit. I'm going to move this resistor down a bit. And then I'm going to add some more, the final two components. So there's a capacitor. Actually, there's final three components. So a capacitor. So I'm going to type in capacitor. And you see lots of CAPs come up, but actually all we want is C. So we look around and we find the one that says capacitor. Now we want a normal unpolarized capacitor. So I'll go for this. And I'm going to go actually with a small symbol, just because it's the first one that came up. It doesn't really make any difference. Again, there's no footprint in there. I'll double click that and I'll select it. I'll put it where I want it to be in our circuit. And then I'll edit its properties. So again, either E or right click. And select properties. The value is 10 nanofarads. And the footprint. Well, this time we need to look for capacitors. Capacitor, THT, through-hole capacitors. And we scroll down And what do we want? Well, CP means C polarized, so we don't want a polarized, we want an unpolarized. So a ceramic disc, that's what we're looking for. Ceramic disc, diameter 5 millimeters, width 2.5 millimeters, lead pitch 5 millimeters. That's actually what we want in terms of this particular capacitor. You can select all sorts of different ones, but that's the one for this circuit. So let's double click that. That's appeared there. So I can save that, and there we go. We've now got the capacitor. Now the other things we need are the connectors. So again, here, connector. Now connectors can be generic or they can be specific. In this case, I think we want a connector. We want 2 pins, single row. So that's what I'm going to use. However, I would like to have pin 1 is ground. So as you can see, pin 1 is on the top at the moment, pin 2 is on the bottom, but I want to put ground on the bottom of the circuit board. So right click, mirror vertically. There we go. So we've now got pin 2 on the top and pin 1 on the bottom. Now the other connectors that I'm going to use are not going to be real connectors, they're going to be PCB pins. So if we go to connectors again, just a second, that was the wrong bit, generic. Actually we want 1 pin, and the reason we want 1 pin is because we're going to make it out of a PCB component. So I'm going to select that, and I'm going to call that one the input. Now that input needs to be pointing the other way, mirror horizontally. But oops, what do you notice about it? It has no footprint. So we need to select a footprint. And we have various choices of connectors which we could use. But I'm going to use a PCB connector. So we've got various possible ones we can use. In this case I'm going to use a pin, a simple pin, or a pad. I'm just trying to find the right one. Give me a second.
I think while you do this, if I may, I'm sure for many of us who've just sketched out a circuit board on a piece of paper, thinking, oh, this is a very long-winded way of doing it. But of course, what we're doing, to remind everybody, we're actually going to use this schematic that you're creating to convert it very easily, as you'll show, into an actual printed circuit board. So although this may be a bit quicker than doing a design on a bit of paper with a freehand, this is going to save us a lot of time later, isn't it?
Yes, exactly. Yeah. So we're going to choose a connector that's going to be a pin, and we'll go for a fairly large pin with a 1.3 millimeter diameter. So there we go. That's our input connector. And I'm going to duplicate that again. If you remember, Control D or right click with the mouse. I'm going to put that one over there and again mirror it because it's pointing the wrong way. So there we go, our input connector, our output connector. Now this connector here, you may remember I didn't give it a footprint. Actually I'm going to use a pin header connector for this. I'm going to use a Molex connector. So Molex are in the library, and the particular one I want to use is a KK254 2-pin vertical connector, one of those. So at this stage then we've got all the components there, but we're missing a crucial one, which is the ground symbol, or power symbol in fact. So I'm just going to add that. There are plenty of power symbols available. The obvious one is to call it ground. So let's place that as well. And now we've got all the parts. And we need to wire them all up. So let's get to doing that. You wire things up using add a wire. And this is the tool for doing that. So I'm going to connect all the bits from the schematic. And you notice that we've not got things particularly well aligned here, have we? Well, we can fiddle around with that and move things about. So I need to look at this one here and think, well, that needs to be a little bit higher up. So I'm going to move it up a little bit. And we can, in fact, align them using a grid. I haven't spoken about the grid yet because I'm going to cover that in the PCB design. Now we can also set a width for that bus. Now that bus, or wire, is going to be carrying quite a lot of current. So it needs to be relatively thick. And an aside for that would be to actually show you how you calculate that, which I'll do in a moment, but let me for the moment just set it to 2 millimeters. And you see it comes out looking relatively thick. Now these connectors, these wires for these particular components don't need to be as big. But first of all let me put in this one. So this is the output. And I'm going to double click on it and set the value of that to 2 millimeters as well. So these are the high current parts of the circuit. Now you see that is not really in the right place. Now there's a function called drag, and that allows you to move things about, and it will adjust the wires appropriately. So that's what I've done there. Now this component here, this resistor, connects to that wire. I'm going to move it down a little bit and just put it down there, and I'm going to move this one down a bit as well to compensate. So we're going to do a wire for these ones. Now there's another wire. This one I haven't set the width for yet. That doesn't need to be anything like as thick. So I'm going to make it, I don't know, 0.5 of a millimeter, relatively thin. That's more than enough for a 10K resistor. It's not really taking much current. And similarly, I'm going to do this with all the others as well. But I'm not going to, at the moment, set those widths. So at the moment, I'm just wiring up the circuit. As per the schematic.
When you bring a drag a wire like that, Mike, and you go over the top of that, does that automatically make the connection, or does it, like when you're drawing it, sometimes you want to skip over a wire? How do you actually make that junction?
Right, so if you click on it, it will make the junction.
Okay.
If you don't click on it, it won't, but you've also got to be very accurate. So let's make this really big. If I click here, so you see the wire isn't connected there.
Right, yeah, that's what I was wondering about. Okay.
Yeah.
Yeah, I see that.
Now if I click there again and join those together, then
they're
they
like
can
one, effectively.
Exactly,
so,
yeah.
Yeah, so if you drag them, then they'll keep connected.
That's right, and I don't know if you can see that the cursor's moving in jumps. That's a thing called the grid. You can set the grid to what you want. I've left it on the default quarter of, not a quarter, a 40th of an inch. Sorry, 0.025 of an inch rather. You can set that to what you like, but because all the components are designed assuming a 0.63 millimeter, 0.025 inch, it's best to leave it at that unless you have a particular reason not to. So, oops, let's do it again. Incidentally, sometimes you make a mistake, and I'll show you what to do when you make a mistake, because I've been known to do that, and I suspect other people have as well. So I've just connected all these together. So there we go, that's the circuit wired up. But let's say I accidentally connected a line from there to there. What do? Well, what I can do is I can select that, right click, delete, and it's gone. So there you go, that's solved that issue. So it's relatively easy to modify the circuit. And the other thing you can do is you can start to make things look pretty. I'm not going to spend a lot of time doing that, but for example, I could drag this transistor up a bit and get rid of that kink in the line there, so it looks a bit better. And similarly, I could drag this connector up. There you go. So it's all looking a bit more aligned, let's say. And that's the whole circuit. So we'll save that. Now, remember that I didn't select all of these buses and set the width. That really doesn't matter. It'll set a default, and you can set the default to what you want. And I'll show you how you can change that. So this is all done in the setup. It will come up with a 0.25 millimeter for all of these connections as the default if you haven't set it to anything else. And now we got our schematic. So well, what are we going to do with it? We're going to try and create a PCB. Now, let me just adjust the size of this a little bit, because a few of the icons have disappeared off the end because I'm doing it very big. This icon here actually starts creating the PCB and loads it with the components. But the first thing we can do is we can look at all of the fields and make sure that we've got everything right, because if you find that you've not got a footprint, for example, then when you come to the PCB it won't work. Now, the other thing is I've missed some things out here, and I did it deliberately, and we'll find out when we go to the PCB well, let's see if you can work out what it is. But if I click on here, this will open that board in the editor. Now what you will notice is there's nothing there yet. That's intentional. You can load the PCB with all of the parts, and it will do that, and it will come up with those parts, which you can then put somewhere in the workspace for your design. Now again, we have this dialog box where we can give it a name and a revision number and a company and anything else you might want to do for when you come to share it with the people. But we've got all the parts here. Now what do you do next? Well, how's this PCB going to look? We can get some idea of how much space it's going to need by looking at all the parts. And I noticed that we've got a square about this large. So we need to make something that it will fit in. And we also need to think about the box and mounting it. Well, that's actually pretty small. And what I can do, I'm going to explain firstly that you need to have a PCB cut out, and this is where we come into layers. So I'm going to select the layer edge cuts. Now a layer is a layer in the board stack up, which effectively will translate to a file that's sent to the PCB manufacturing for each one of these layers. And edge cuts is the one for the PCB design. So if we create a rectangle in that board, like so, that can be our PCB. Now, I can resize that. I can just click on it and drag it, make it bigger and make it smaller. But the other thing I can do is edit it. And what I generally do is set a start point and an end point for the size I want. And I reckon that this would probably be about, I don't know, 40 millimeters by 30 millimeters, something like that. So if I set the start point at, say, 120 and the end point at 160, and do the same with the Y dimension, so let's set that to, say, 60 and to 90. There we go. That's our PCB routing area.
So again, to remind everybody at home, at this stage, all those components that you put there, because you spent time choosing the right footprint for them, not just the right schematic symbol, but the actual footprint, that means that these are already representing their real scale size on the circuit board.
Exactly, yes.
Okay.
Yeah. And again, there's a grid to the circuit board, so when I come to position them, I can position them where I want. And we have to, I don't know if you can see, but very thin lines have appeared. Those are the net list, the nets, which show what's connected to what. So when you come to lay this out, you can then, let's move it into the middle, you can then decide, okay, that one needs to go there and this one needs to go here, and that one will wire up well if we put it close to that and turn it this way around, etc., etc. So all of the different layers are in this list here on the right hand side where I'm moving the mouse now. And the thing is, you can turn them on and off as well to make the board look clear. Now, there's a lot of these grey symbols, I notice, which are tending to confuse me. And there's also the silk screen, which is tending to confuse me at the moment. I might want to see the silk screen or the grey numbers, but I don't want to see them both. So what I'm going to do is I'm going to turn off the grey, which is actually called front fabrication. And normally you don't actually have that layer. When you go to a fabrication house, you don't need to have that. This is for assembly of a board. So if I click on that, that turns that off, and suddenly it's a lot clearer. You can see what you're doing. And then we can go into the design. So just move parts about, really. This is the transistor, and the tab is actually in the right place at the top. I want that near the edge of the board so I can fix it to a heatsink. So I'm going to put it there. And this is my output connector, PCB pad. I'm going to put it there, and I'm going to put it there because I want it to be very, very close to the transistor because it's taking a lot of current and I don't want to have a voltage drop. And this is the input side. And I can do the same with that. And you can see these wires. So that's how I know it's the input side. I can see it's connected to the center of the transistor. But let's put that there. And once we've done that, then we can think about where all the other parts are going to go. And it's up to you really where you put things. But we've got 4 resistors. We can have them horizontal or we can have them vertical. We can move them about. I think they'll work better. I know they work better if they're vertical. So I'm going to put R1 here because that's associated with that pad on Q1. So let's just put it here for sake of argument. Now it's not going to go on top of R2. We're going to move R2. If I put it that way round, that should work quite well because R1 and R2 will be wired closely together. But, well, is that best? Maybe, maybe not.
Now, of course, if this was we're being radio amateurs, a lot of the time we're designing with radio frequencies, and of course then the layout may be much more critical than on something like this, which is essentially a DC switch, isn't it?
Exactly, yeah. So if you're doing an RF board, I did an RF board on the BATC demo, you need to think about the track widths being 50 ohms, and you need to think about having all the RF connections short and the ground plane and everything else. For a switch, you don't really need that. So I'm just going to put these 2 resistors here for the moment.
And again, I'm just going to say, for the sake of people at home, we've got a very high resolution monitor here remotely linked to Mike, but I know this is going through a streaming process. You may not actually be able to see some very, very fine, almost hairlines between the components, and these, as Mike said, but you may not be able to see them at home, represent the net list, the way these components are actually connected together. They're going to cross over each other and all sorts of things at the moment, and Mike will show us how to sort that out. But it's important to realise these aren't just moving the components away. Those that virtual wires, those very, very fine wires that we can see, you may not be able to see at home. Just thought I'd point that out.
Exactly, yeah. So, unfortunately, I don't really know. Sorry, having a bit of a cough.
We're just actually looking at a monitor here, monitoring what we're streaming out. And for example, on BATC, you could just about make those fine lines if you look at it close. So, depending on what you're watching this on, do have a close look, and you'll see these fine lines. It's quite important to the demo that Mike's giving.
I'm turning them on and off again. I don't know if you're seeing that.
Yes.
Okay, so back to the circuit. I'm going to move R3, and I see it's connected to the transistor there. I'm going to turn it around as well. Put it there, and R4. And I'm going to put it there for the moment. And then we can see all the different lines. This capacitor needs to be near the connector because it's for RF purposes. Stop the RF getting into the circuit. I'm going to put that there. I'm going to move this. Oops, that's just moving the label. Sorry. I'm going to move this connector and put this connector here on the other side of the board. So there we are. We've got a rough layout, which may or may not be right. And if you could see these, if you can see these lines, you can see roughly where tracks might go. And I can see, for example, that there's one crossing over here and one crossing over there. It would be better, and this is what you see from the net list, is if that was turned the other way around. Now, you know, you get a feel for how to lay things out, but that comes with experience. And laying out something like that looks like it might work, but let me zoom in very close. I don't know if you can see, but ground is here on this connector and ground is here on the capacitor. Well, it would be better if they were aligned up, if you think about putting a track through that. So I'm just going to rotate it around and move it back into position. There you go. Now what you can see is the label has sat on top of the other one. You can just select the label if you just click on that, and you can move the label and put it somewhere more useful. So we're going to put this in a box, but this is where I come to the thing that you may not have noticed. So I'm just going to save it. There are no mounting holes. And you think, how do you put a mounting hole in? Well, actually, you do it from the schematic. A bit counterintuitive, perhaps. But let's just close that down, and let's go back to the schematic and look at it full screen. Everything goes on the schematic, mounting holes, logos, all sorts of things. So what I'm going to do is I'm going to add a mounting hole. So there we go. It's come up with the add component again. Mounting hole. And mounting hole with connection or mounting hole without connection. So with connection it would have a pad which you might connect to ground, for example. This is a high voltage board, so I'm going to make it without a connection. So let's add that. And then let's look at its properties again. And notice it hasn't got a footprint. Well, what sort of footprint do you want for a mounting hole? You probably just want a hole, and that's included. So these are the different types of mounting holes you can get there in KiCAD. What size, etc. M3, M2.5, M2.2, M2, right up to M8. Well, M8 would be too big. Typically M3 is the size we use. There we go. Now, we probably want more than one mounting hole. And again, duplicate. I've got 4 of them now. But one thing I forgot to do is in the properties, I don't know if you can see here, there's a thing called exclude from bill of materials. I really don't want to go to DigiKey and order a mounting hole. So I will click that exclude from bill of materials. Now I could do that for all of them, but remember the shortcut where you can look at things in general? Well, you can do that here if you want.
So that's now creating a sort of bill of materials, or what we might normally call a parts list. All the things that we might need for this.
Yes.
Is that right? Yeah.
Yeah.
Okay.
And those are all our mounting holes. Anyway, let me just say OK to that. And then we go back to our printed circuit board. Now, again, this icon up here allows you to add things that were not there. So if I do that, we should now have our 4 holes. And we have to decide where to put them. Incidentally, the round purple parts around all the components are the clearances. So if you put a hole there, you don't want anything within the purple circle, because that's where the nut or bolt is going to go.
Just a quick question coming in on YouTube from David Esser. Just says, can the mounting holes be duplicated on the PCB? Or do you have to do it on the schematic?
You can do it on the PCB. You can then update the schematic from the PCB the other way around.
Okay.
If you want to do it that way. I find it easy to do it this way, but you can do it the other way, yeah. And I'm just putting them there. And actually, because I've got a grid set, they are moving. But my grid is actually probably imperial at the moment. I've got it set to 0.01 of an inch.
If I may just remind everybody at home, unlike normal regular talks that we have on Tonight at 8, when we encourage people to ask questions at the end, because this is a live demo that Mike's doing right now, if you do have a question while he's doing something and you just want to know something about that, probably easier if you ask it right away, and I'll keep watching those and we'll read them to Mike at any time. Thank you.
Yeah, indeed. So I noticed this connector now is a bit close to that hole. So I could make the PCB bigger, or I could move the connector. So I'm going to move the connector. And similarly with that connector, give us a bit more space. Now that's our PCB laid out. And we can change this, incidentally. There's no reason it has to stay like this. But spend as much time as you like trying to get it looking about right for the tracks before you try and put the tracks in. Because putting the tracks in, once you've done them, you have to undo them if you want to change anything. Now let's talk about tracks. So PCB has 2 layers. One called front copper, which is coloured standard in red, and one called bottom copper, which is typically coloured in blue on the screen. So you're looking down from above, down on the PCB. I'm going to do most of the wiring on the top of the PCB, and there's a reason for that. It's because normally I do RF PCBs, and they are typically one side is ground plane, the bottom, and the top is where you put the tracks. If you're doing through-hole PCBs, you can do whatever you like.
And again, if you don't mind me, just for the sake of those really beginning in this sort of thing and maybe never considered a circuit board, some printed circuit boards are single-sided, which just means that there's copper on one side. There's no copper through the holes and there's none on the top side. But as Mike said, this particular board is going to have 2 sides. There's copper clad, as it's called, both sides of the circuit board, and we're going to use both those sides. Years ago as well, I would just add, if you were going to make your own circuit board, it was incredibly difficult to hand draw and line up both sides of a circuit board to etch yourself using ferric chloride or whatever, whereas now when there are manufacturers, as we'll talk about later, who are doing this sort of thing, it does mean that double-sided printed circuit boards are quite easy to get made for you. Back to you, Mike.
Yes, indeed. Okay, that's true. Actually, it's much easier to make a PCB these days. Now, I'm just doing the wires here, and you notice how thin they are. That's because that's the default wire size. Now, what you can do is you can either go back to the schematic and set the wire size for each bus, or you can edit them. Edit predefined sizes. So what I'm going to do is I'm going to add a track, not of width 0 millimeters, but of width 0.4 millimeters. I'm going to add another one, 0.7, say another one of 1. And let's put another one in 2. So that now allows me to set track sizes. And if I go to this track here, I don't like that, I'm going to delete it. I'm going to draw another track between those. I can then change the track width, and I can do that either with the mouse or by pressing the W button to scale through the different sizes that I've got. Now that's far too big, that's too small, that's really too small, that's probably about right. So that is a 0.7 millimeter track. If you've got something that has to go between pads, you probably need to use a smaller one. And I can see from these lines where this needs to go, but also as you click on it, what you are trying to wire to is highlighted, so it helps you. And it also automatically allows you to see what's connected to what. So
again, how are you highlighting it, Mike? What keys are you pressing?
It's done by the software.
Right. Okay.
So I'm not actually highlighting it. Now we're going to come across a problem here, because if I try and put that one in and then I try and put that one in, they're going to cross or go around each other, which doesn't look particularly good. So what I'm actually going to do, I'll delete that. Control Z, by the way, for Windows users undoes what you did last time. I know that if I rotate this resistor, it'll be a lot easier to wire. And some of those things you only discover once you're trying to wire it. So if I now try and wire this up, I can wire from here to there, and I can wire from there across to there. I'm not going to do that one yet. But of course this one still needs to go to that one. Well, there's two ways of doing that. One is to keep it on this side of the PCB and just go like this. Whoops. That doesn't look very neat, does it? Actually, if you redo it, it will take account of that and it will redraw it for you. So there you go.
On the subject of neatness, Mike, if you don't mind, I did encourage people to ask questions as we go along. Pete M0OFM says, for those of us with slight OCD tendencies, is there a snap to grid function to help align the edges of components on the circuit board?
There is. In fact, I'm using it now, which is why they're aligned. And you can align them to as tight a tolerance as your OCD requests.
Okay, so the grid that's there that you can't quite see until I guess you've got more of a feel of it, Mike, because you're moving your mouse and moving things, but that will let you snap things to exact differences. And you talked about setting the grid earlier to whatever you want it to. So.
In fact, you can see it moving in steps.
Oh yes, yeah, we can see it there. If you move it quite slowly, actually, Mike, if you can move it a little bit slower, that's it. I think people can then see it's moving in steps rather than continuously moving.
Yes, it's a very fine step. So the step between component pins is typically 1/10 of an inch. This is going in about 1/50 of an inch at the moment. And you want it much finer just to ensure that you can align the tracks. Now, one thing you'll notice, by the way, is I'm not wiring up any of the grounds because I intended to use a ground plane on this board. I'm just going to do this, a few more of the tracks, just to finish off. And incidentally, down at the bottom, it will tell you how many lines you've got unrouted. So I've got all the grounds are unrouted at the moment. I'm not going to worry about those. And in fact, I could, if I wanted to, hide the ground connections so that they don't get in the way, which is what I do when doing a complicated board, because you don't want to see all the ground connections. But we'll leave them here for the moment. And then we've, oops, I managed to start a track there. So again, I'm just going to wire up to there. And for this one, up to there. Now, here to here, that's a very thin track at the moment, but actually, if I use the netlist track, that would be 2 millimeters wide, but it's actually currently 0.5 millimeter wide. I'm going to show you what I'm going to do about that in a second. And similarly, this one to here, I'm going to do like that. Now, those would carry high current, but don't worry about that. I'm going to show you what to do about that. And I'll do that now. So there's a thing called zones. And we're going to draw, this is this one here, add a filled zone. If I click on that, and I'm on the front copper, and I say go from here, and click on it, I can say what net I want this filled zone of copper to be connected to. And I want it to be connected to this net, which is actually, if you search for it, J3 pin 1. The other thing I want to do is I want to turn off thermal reliefs. So thermal reliefs are things that you put on the PCB. They're basically gaps to make soldering easier, so that all the heat is not wicked away by the copper board. Normally you would want those, but when we're trying to deal with high current, we don't want those because they reduce the current carrying capacity. So I'll show you what those are in a second by turning it on and off. But I'm just going to draw an area here. And can you see that hashed mark there? That's a filled zone. And I'm going to do another one for the other side.
So when you talk about a filled zone, Mike, what do you mean? Is that going to be a solid piece of copper?
It's going to be a solid piece of copper, yeah.
Okay.
So filled zone will start, it's going to go from where? Actually, I just did that wrong. Let's just edit that a second.
That's a great way to show that you can undo things.
Yeah. I've just selected it again because I actually wanted it not to go to there, but to go to there. And I seem to have ended up with an extra corner, which I will take out. You can just click on these corners and move them up and down. So that's going to be a big area of copper on the board. And to show you what happens, I'm going to fill that zone. Now, you fill the zones on this side of the board, strangely enough. But there you go. That's now filled in. And I don't know if you can see. Let's go in really close. It's left a gap around this track where it's not connected to that net. So that's not going to short out. And it's left a gap here.
So even though it's a lighter shade of red, that is going to be one big mass of solid copper, yeah?
Yes.
Okay.
Yeah. The reason it's a lighter shade of red is to allow you to see the tracks underneath it. And actually you can edit those things. So I can make it darker like that.
So because effectively you're not going to see that smaller track or thinner track, are you?
That's right. So I can turn that up and down. So let's leave it like that. And then let's do another one on the other side. So we need to move over slightly. We need to select filled zone. Make the first click. It will ask us what we want it to connect to. And that is junction 2 pin 1. Now, again, no thermal reliefs. and that's done another filled zone, which is going to be connected to those tracks. Now this is where we could start thinking about beautifying things a bit, perhaps. But let me just, well, firstly, let me just fill that in. Incidentally, you can fill a zone by pressing the B button, but that's not at all obvious. But you can see this track could be better laid out. So let's try again. There we go. And if I refill the zone, that looks a bit neater. So the point about doing all of this is to leave a large area of copper to carry a high current. Now, remember I said that we hadn't done the grounds at this stage. So how could I connect all these things that are connected to ground together? Well, the answer is another filled zone. But let's do that. Start here maybe. But this time we'll put it on the bottom copper and we'll connect it to ground. And we'll leave thermal reliefs in this time because this isn't carrying high current. So let's do that. So let's draw this box.
If you've never done anything like this, by the way, at home, you might look upon this more, almost like a puzzle. I used to find it quite therapeutic, although it could be extremely frustrating if you'd run out of space to put in, and you were doing two sides of a circuit board. It was before the days of when you had multiple layers available, but it is like a puzzle. In fact, Stuart Baker's watching this, and he said, "Couldn't you swap R1 and R2 and then make them 180 degrees out?" And so he's obviously thinking of it like that as a puzzle. It's how to make it neat and using the shortest tracks, etc., isn't it?
Exactly.
Do you enjoy doing it, Mike?
Oh yeah, well, it's very therapeutic. It's a good way of reducing stress, actually.
Yes, that's what I used to find.
I mean, so if you look at this now, you notice that, I mean, I didn't quite get that zone right, but I can edit it. That's the main thing. So if I don't like the way it's set, you know, if they're not quite straight, for example, I can move things around. So I've just done that there, but I think that's fine as it is now. And if you look, if I fill it in again, you look here, we've got no unrouted nets now. That's connected all the grounds together just by doing that. And the other thing you can see is the thermal reliefs. Now,
Right.
Can you see those
Yes.
things there? That's thermal reliefs. And just to show you what a non-connected pad looks like, that's what they look like. So they're not connected to the ground.
And just again for beginners to this, if you didn't put those in, those thermal reliefs, if you were to try and get a soldering iron then and heat, say to solder or desolder one of those resistors, not only would you be trying to desolder or solder that one little pad, but you'd be trying to heat up that whole lump of copper, which of course would spread the heat and make it much more difficult to do. So that's one of the reasons you do it. And we should just point out as well, Mike, can you just go over again that you're using blue now, because that's the other side of the circuit board, isn't it?
That's the other side of the board, yes, that's right.
So red is represents one side of the copper on the circuit board, and blue is the other.
Yeah, nominally red is top, blue is bottom. I guess it wouldn't make any difference if it was the other way around. But yes, that's right. So
just to try again, sorry Mike, just to interrupt again, but we're trying to make this interactive with everybody at home. Alan M7ASJ has made a mention here of something that you might want to cover now, and says, what about heat sinks? Because of course you couldn't we, the copper to act as a bit of a heat sink as well?
You can, and you can use filled zones as a heat sink as well. The thing about PCB is it takes quite a few square inches to dissipate a watt of power, and this transistor, which is the only thing that's going to be getting slightly warm, has got a big tab on it, so it's generally better to put that on the side of the board and bolt it to a heatsink. But you can use PCB.
If something's just getting warm, maybe it's another good use of a bit of copper, isn't it? Yeah,
it is good use of copper, and you can also get little PCB mounting heatsinks that you mount on the board. So transistors typically are sort of turned on as switches; they don't dissipate much power, so you can use those. with a relatively small area of copper because they don't need to dissipate much power. What I'm going to come on now then is the labeling of things, because with all higgledy-piggledy at the moment. And I guess you can see, if I select the front silk screen, then this will highlight these different layers. And I want to move all these things. And this is why I'm going to show you a shortcut as well, because one thing I don't want to do is start moving components around when I'm trying to move labels by accident. So what you can do is, in the selection filter, you can select all or none. Then you can select just the text. And if I try to select something, I'm clicking, but nothing's happening until I select a piece of text, and then I can just select the text. So that's a useful thing to do if you need to just select a particular thing. And you could just select a footprint, or just select a track, or just select a zone. So I'm going to move this Q1, which is currently off the PCB, and I'm going to put it, say, here. I'm going to move, well, R1, C1J, they're okay. R3 though, it's a long way up, so I'm going to rotate it. I'm going to put it on top of the resistor here. Shall I put it on the top or the bottom? No, let's put it on the bottom. I'm going to put it here. R4, R2, R1. I'm going to move this J1 to here. I'm going to move J2 to here, and I'm going to move J3 to here. But more about that in a second, because we've got a hole here, so we've got a label for a hole. It's a bit daft, isn't it? If I right click on that, I can edit its properties. I can make it not visible, so it doesn't come out on the PCB.
Now again, just thinking beginners in mind, sometimes when you see a printed circuit board, it has these labels on them, and sometimes it doesn't. And years ago, again, if you did it yourself, I doubt many of us would have ever contemplated putting on a sort of silk screen layer, as we sometimes call them, on a homemade one-off printed circuit board. But with the manufacturers that can now produce these things very cheaply in volume, it's almost free to have this done, isn't it? And just one other thing, if I might just put in, as some people may see a term called annotation, and that is the technical name that most manufacturers would use for this, what we're calling labeling. So if you see annotation and wonder what that means, that's generally what they call this layer, isn't it, Mike?
It is, yeah. And of course, you don't just have to stick with these labels, because there's a tool, the text tool, which allows you to add text, and that might be useful. So for example, you might want to have in, and you can set the size, the width, the height, and the thickness. So it's currently set to 1 millimeter by 1 millimeter and a thickness of 0.15. I can put that there, and that says in. Now actually that's a little bit small, isn't it? So let's change that. Let's make it 1.5 by 1.5. And I'll make it a little bit thicker, 0.25. There we go. And I can move that about. So now we've got a label saying in, and rather than do another one like that, I'm going to select it and duplicate it, and I'm going to move it to in. Of course, there aren't two ins, so I can edit that and change it to out. And there we are. And let's position it roughly right. And then we might add another one, and we'll call that control. So we've now labeled our various ports, which will be useful when you come back to it several years later. And you can do other things as well. You can set it to whatever you like. Now you can write a thesis on the back of the board if you would like, if you want to. There's all sorts of things you can do.
So you can put your call sign and which version it is and things like that as well.
Yeah, exactly, yeah. So I could, for example, put here G0MJW version 1.0 2024. And where are we going to put that? Well, let's put it... Sorry, I deleted it there by mistake. Let's try again. G0MJW 2024 version 1. Slightly different order, but never mind. And rotate it and put it there. Now the other thing, of course, it doesn't have to be on the front. So it could be on the back of the PCB. If I did that, I could put it onto a back silk screen. But if I put it on the back silk screen, I need to reverse it so that it will read correctly. So there you are. It looks backwards from the front, but it'll be the right way around on the back. And maybe that's, there's all sorts of things you can do here. So just looking at this now, we finished the board, but I noticed a few things, and you've got to inspect these things very carefully. Like I didn't get the holes in the right place. Now I want to select the holes, so I'm going to select all items again. And in fact, let's just select footprints. That hole wasn't quite aligned, and neither is that one. I want them to be just inside the PCB. And if you want to get them precise, you can actually set the values here. So you can set the spacing. So let's say you wanted the X position to be exactly 156 millimeters and the Y position to be exactly 86 millimeters. You can do that. And then we edit that one. And we set that to 86 and 124. So now we know how far apart those holes are when we come to drill our panel to mount them, which makes life a lot easier. And the reason those weren't automatically in 1 millimeter spacings was because the grid size that I'm using is is imperial rather than the metric for placing the components. And again, you can place the components on a metric grid, but if you do that, a lot of components are actually imperially spaced, yes, so yes, it makes wiring them up more difficult.
Absolutely. I mean, the pitch, as we call it, the difference between them of connectors, for example, is still 0.1 of a pitch, isn't it? Or 0.1 of an inch, rather, or made up of a multiple of that.
Yes, exactly. Yeah. Now, the other thing I notice is these two pads here, they're taking the high current. We've only got them on the front, but there's no reason we could only have them on the front. We could have them on the back as well. And I can edit that and put it front copper and back copper. That'll immediately give me twice the current rating. And I can do the same with this one. And I can refill them. And now can you see they're on the front and the back? Maybe that's difficult to see. But if you want to look at the back of the board, you can actually flip the board view and look at the other side of it. And now you can see the text is the right way round, but all the other text, of course, is the wrong way round.
This looks like one of those sort of programs that you've really got to download it and play with it. And then I presume when you were doing this yourself now, you've used it for some time and you get very quick at doing these things with shortcuts, etc.
Yeah, exactly. Yeah, and you learn how to do it. Initially, it's a bit difficult, but it doesn't take very long to pick up, really. So that PCB is now pretty much done. One of the party tricks, I guess, of KiCAD is the 3D viewer. I'll just show you that.
Oh, isn't that? That makes all that those details about getting the dimensions of the component at the beginning really worth it, isn't it? And that's all built into the standard KiCAD program, yeah?
It is, yeah. So you can look at that board now and you can see the clearance between various places. And for particular projects, that's actually really important, especially if you want to see if one thing is fouling another. So there's the back as well with the silk screen on it. So it took a bit longer than last time, but that's how to do the board. Now the next thing is, of course, how do you get hold of one? And that's around plotting it. So let me just close that down. So I'm going to save that now, and I'm going to go into the part where you actually plot out the Gerber files. It's in the File menu and under Plot. Now, fortunately, the standard values are just what you need for most PCB houses. So don't worry about any of these, because they're all set up as they probably should be. So you need to choose a directory. What I'll do is I'll create a new directory, and I'm going to call it Gerbers. Gerber, incidentally, is a file format. I'm going to select that folder. It asks me if I want it to set it relative. Well, I do. Don't worry about that. All I have to do is click on Plot, which plots all of the silkscreen, top copper, bottom copper, solder mask, all those layers. But I also need to generate drill files for the holes. So I need to generate a drill file. I usually generate a map file. I don't think you really need to do that. Close it. Again, all the defaults are there. That has created a set of Gerber files in a directory that we just selected. So,
and again, Gerber is the standard, the world standard, isn't it, really, for sending designs of circuit boards to people, and it contains, I believe, all of that information, not only the tracks, the size of holes, and all that sort of thing that a PCB manufacturer needs.
Exactly, yes, it does. Now what I'm going to do is I'm going to bring over File Manager, and if you look, so that's the file that's the folder we just created. Here are all the different files.
So if we just, for again, that's going to be quite small for anybody at home, because it's very small for us here in the studio. So each of those are the different layers and details like that?
Exactly, yeah. They're all the different layers, and I'll show you those in a second. In fact, let's show you them now, why not? If we go back to the main window, there's a thing called the Gerber viewer. If you click on that, then it allows you to view Gerbers. So you go to File, open Gerber plot files. It'll already set you up in the right directory. So let's say we want to look at, let's look at the front copper. That one there. And there is our front copper. So that's what gets sent to the PCB house. And you see this funny little thing here. Now we could probably, and that's not quite the same height as that, so we can go back to our PCB and maybe make it look a little bit neater if we wanted to.
That's the OCD bit again, isn't it? To
exactly,
make it look
yeah.
Neat. Yeah. It's not good to take a pride though.
Yes. Yeah. Well, actually, in this case, there's going to be 50 volts between these 2 points.
Yes,
so we do want to make them a little bit better spaced potentially, but of course we're limited by the spacing on the chip itself. On the TO220, and that should be more than enough, really.
And of course, if we were doing this as an RF design, that could be even more important, because it could add, say, capacitance between two tracks and things like that.
It would. The other thing I was going to show, actually, are the calculator tools. These are very useful. This is for doing microstrip transmission lines. Maybe that's a little bit complicated. But if we go to the power, current, and isolation, and we go to track width, it will tell you how hot the copper will get at a certain current, or
so that's really
alternatively helpful. it will tell you what the maximum current that you should allow for certain types of PCB, 1 ounce copper, 2 ounce copper, and those are things that you set at manufacturing size. So,
so sometimes with a resistor, for example, then most of us will know that resistors get rid of the excess by heat. So if we think that heat that is going to get so X amount hot, 1 watt or whatever, then this will help you calculate how big the piece of copper might have to be to help you dissipate or lose that heat.
It can do that as well. This is about the current carrying capability. So a 0.3 millimeter track will carry an amp relatively easily, which is surprising. But if you want to carry 20 amps, then you need 2, 3, 4 millimeters at least. But yes, I don't know if it does heat sinks actually. It might do. I'd have to look up as where those are. It certainly does useful things like transmission lines, and also allows you to calculate things like pi attenuators.
Wow.
And the wavelength, depending on the type of copper and the thickness of the track and the thickness of the PCB and all those sort of things. And in case you wanted to know it, the resistor color code, all of those sort of things. So useful, and there are various plugins you can get using the plugin manager that do other useful things, which I'm not going to go into now, but things like producing bills of materials or doing RF type components, or with the sort of triangles that you see on 10 gigahertz PCBs, for example. It allows you to do all that sort of thing.
There's some really useful things for radioamateurs here, aren't there?
Yeah, printed inductors particularly are useful.
Yeah.
Anyway, so what you do with the Gerber files is you take all of them and you basically, I'm going to use 7-zip, you could use WinZip, whatever. You add to a file. It's called gerbers.zip in this case.
So that's just going to compress all those files into one?
Yep. You upload that to the PCB Design House website, and that's it. Then, you pay them some money, and you can make various choices. So I guess I think it's okay to do this, is it, David? Show
of course,
one
yeah,
particular
absolutely,
one?
yeah.
So I'm going to use JLC, because that's the one I normally use.
Okay, so that's a company in China, I think.
Yeah.
And one of the things about this is as well that you may wonder how they can produce things, and Mike will show you live here how much this will cost, and it's very cheap. And one of the reasons they can do it is because they make a massive, huge circuit board made up of lots of little designs, one of which will be Mike's, and then they cut it all up at the end of it and send them out. That's one of the reasons that it's a lot cheaper than it used to be, isn't it?
Yeah, and actually there's a very good YouTube video which shows them doing just that. So I've just selected that, it's uploading it, it's taking a while.
We should mention though, as they always say, other suppliers are available. In fact, there's several in the UK still making circuit boards. A couple I know, PCBtrain.co.uk and Minitron.co.uk are British manufacturers who'll do this. Probably will cost a bit more, but then you get it much quicker, because there'd be, in some cases, if you want something really quickly, you can get it done the next day. So
yeah, and it's loaded up by Gerber's. It's analysed them. It's shown me a pretty picture of them, so I can verify that they're okay. And I've got some options now, which I can go through. You can, incidentally, if you choose anything that's not standard, it suddenly costs a lot more. So if you choose Rogers PCB, for example, or Teflon PCBs, they'll be expensive for RF use. High precision, lots of layers.
So the FR4 is just standard fiberglass, isn't it? So the actual insulating material, if you like, is fiberglass, which is what most printed circuit boards in most products are made of, I guess, for us.
Yes.
And then one other thing, I don't think we mentioned the word, and again, I'm trying to help people who may see words and they think, well, what does that mean? And there's a word that's commonly used in industry called resist. And that's that sort of green in many cases, and on this design, that's that layer of effectively a paint or whatever it is on the top and the bottom, which just provides insulation and protects those copper tracks from being just exposed. And that's called resist. So if you see that on a circuit board design or anything, or what color resist, that's because that's what that is called. That layer of extra insulation material just to cover up the copper. I hope you don't mind me mentioning that, Mike.
No, and I was just going to come on to that actually, because what it does is it goes in between pads and stops you shorting them out when you solder it together. So it's very useful to have the resist. And you can choose different things. So you could have green, that's the standard, fastest turnaround. You could choose purple, but purple might take 3 or 4 days, and you see the board's now coming out in purple. Particularly nice is black, which is quite good if you use a PCB for a panel label, for example. It's very clear, but it's you can't see the tracks.
But you can't see the track. I was going to say that's not easy for fault finding when you're designing something yourself. I mean, if you also, I believe this firm and probably many others, if you were mentioning about keeping it standard, if you change to a really obscure colour, you might find that price, which you can see on the right-hand side there, suddenly runs up hugely.
Exactly,
so.
Yes. And the other thing to note is that if it's more than 100 millimeters wide or high, the price goes up quite a lot. So try and keep your PCBs to less than 100 millimeters square if you want a cheap price. And the price is $2.
Yeah.
Now, that's a little bit misleading. So what you can do is you can then save that to the cart. And I sign in here. I've got to tell them I'm not a robot. So £1.59 for that PCB, and the shipping estimate £1.19. So
Amazing.
add those two together, and it's under
£3. Amazing.
Under £4. However, you have to add VAT to that, and you have to add sort of a insurance and PayPal fees if you use PayPal, which is the normal way to pay. And by the time you've got all of that done, it's going to cost you a £5. But really, that is incredibly cheap. And incidentally, I didn't mention you actually get 5 for that price. So I'm not going to buy those because I don't want to. Well, I'll deal with that later. I'll just close down that web page now. So that's pretty much all I was planning to show.
So there are other suppliers. That's one of them. You said JLC. There's another one in China called PCB Way. I've used those and they've been quite good. And as I said, there are British firms as well who manufacture circuit boards like this. But the important thing, I think, is to explain this is how really it used to be industry would go this route and email files, but now you can do this at home. And this software, again, Mike, is free, isn't it? Completely free?
Completely, yes.
We can just show you now. We're just going to put a caption up now to show you where you can get this software from. Here it is. It's KiCAD.org, KICAD.org. So it's something you could download and have a go. So we encourage questions as we have all through. We haven't got any outstanding at the moment. I've got a couple, Mike, for which, well, one actually was asked a minute ago, and I think we should mention that if that's all right. I'll ask you that in a moment. But one other thing we didn't mention are the things called vias. And again, I think for maybe the average amateur who's not been in industry, they may not wonder what is a via. But of course, sometimes when we talked about this puzzle, I wonder if you could get that up, Mike, and do you mind demonstrating what this is? So.
Yep.
When you have a circuit board like this, it's like this puzzle that we talked about, but sometimes you just can't make the tracks all make up, can you? Because they have to cross over each other. Now, if they need to cross over, of course, you've got the other side of the circuit board.
Yes.
That means we've got to get to the other side of the circuit board, and we do that through a hole which doesn't have a component in it, and that hole is filled with copper, and that's called a via, VIA. So if you see that written somewhere and you wonder what it is, that's what it means. Mike, I wonder if you'd mind demonstrating to us, maybe adding a via?
I could do that actually. So this is a bit false because obviously the hole on the resistor is on both sides anyway. But let's assume it's not for the moment. So I'm drawing a track and I need to get to there. Then I can't get over that track. So what I will do is I will add a via, and you do that by clicking V in KiCAD. So that goes through the track. If you then follow the track from there, but instead of doing it on the front copper, you do it on the bottom copper. So select the bottom copper. There we go. And can you see now I've joined those two up?
So we've gone from one side of the circuit board to the other to make that sort of like a link, like you might do with a piece of wire normally.
Yes.
And then join it up. Of course, you'd have to change then your blue big arrow, wouldn't you?
Yeah. So I have to refresh that.
Lovely.
And you can see that's done that. Now, actually, when you're designing a PCB that's complicated, you very quickly get tied up in knots. So the way to resolve that is to set yourself a rule where you do horizontal tracks on one side of the board and vertical tracks on the other. And that will allow you to route most boards on 2 layers relatively easily. If you start waving around like I've done here, because I knew it was a simple circuit, it rapidly gets very difficult to route, and you end up unable to do it. So that's the way to do that: horizontal on one side and vertical on the other.
Yeah, good point. So that's that puzzle, though. It is, as Mike said, it is very therapeutic to do this. We've got a question. I'm sorry I missed this from earlier. This is from Steve M1SDH, who asks, do data sheets for components have details for recommended footprints? For example, the pitch. So do data sheets have them?
They do, yes. Usually.
Okay.
I haven't got any example data sheets to hand, but typically a component will, especially an RF component, but also a lot of surface mount components will have a suggested layout as well. So they won't just have the component, but they'll also say where they suggest you put the capacitors and the inductors and the resistors along with that as well.
Okay. Lovely, thank you. Moving on to questions. This reminder again to everybody at home now. You've hopefully been following this. If you joined us a bit late though, you're welcome just to ask questions. Mike has started from the basics of just entering this as a schematic diagram, the basic circuit diagram, and converting it to a circuit board. But if you've got any questions, now is the time to ask them either on YouTube chat or BATC. Richard G8UNO says, hi Mike, would you mind telling me all this 30 years ago, because it would have saved him so much grief with CADstar, Pineapple, Boardmaker, DesignWorks, Eagle, Osmond, Fusion 360. I wish we could just see what the world back then, but yeah, I can recognise some of those words. What about you, Mike? Was your experience?
Well, yeah, I started with I think CADstar.
CADstar, that's a classic.
Long time ago.
Yeah, and very expensive as well.
Oh yes, yeah, they used to cost thousands of pounds, these packages, and you need a fairly good PC. I think the first time I saw PCB design software was at the BBC when we had a visit in about 1982 when I was just starting at university, and they had some very expensive, I expect, computer that could do this sort of thing. But again, very basic by modern standards. What I haven't gone into is all the simulation that KiCAD can do as well. It can simulate components, and you can see how a circuit would behave if you put all the right parameters in there for the parts. So making oscillators or HFRF circuits, you should be able to simulate those.
Yes, excellent. Thank you. One other question actually leading from that, and in fact someone mentioned it earlier on, is surface mount, because if you've been designing your own products, or if you've tried just looking around for components now, as well as these which are called sometimes conventional components or wire-ended or wire type components, you have things now called surface mount components, which makes our electronics so much smaller. And indeed, I think you'd agree, Mike, some chips now, some products released are only available in surface mount. So my quick question, could you give us a quick demonstration, sorry to put you on the spot, of say putting a surface mount capacitor or resistor on here?
Yeah, in fact I can probably do better than that. If I'm sorry my video keeps freezing, by the way.
It's a bit juddery. That's why we've taken it off the screen, so sorry about that. But
I fixed it again, but
but we can hear you fine, but it is a little bit juddery, your actual vision, so that we've just taken it off the screen for now.
Yeah.
So again, just to tell everyone at home, so conventional components that like they've always been with wires at the end, that's fine, that's what we've dealt with today. But nowadays we do need to use surface mount sometimes, especially with RF designs, and there are components which are basically the raw component with a bit of solder or a bit of something connector at each end, and you mount it on top of the surface. So there are no wires that go through holes. That's by the name, as the name suggests, surface mount. And what Mike's going to show us now, it looks like he's going to maybe change one of the components to being surface mount. So for those somebody who asked that,
so I'm just going to change this transistor from a BC546 to what would be BC846, which I think is the surface mount equivalent of that.
And I'll be coming to your questions, Andy, and Peter as well in a moment. But let's watch Mike put some surface mount on here.
Yeah. So just to show you the footprint now, it's a surface mount footprint rather than a through-hole footprint. So that's now a different component. If I go here and I update the PCB, Q2 has vanished and been replaced by a surface mount one. So now what I would need to do is delete some of these tracks and position this transistor.
So this is where they've got these pads, as we're calling them. They haven't got holes because, of course, you're going to mount the transistor onto this side of the circuit board only.
Yeah, so you can see there are no holes there. Now it's going to be fairly simple to wire up because this pad will wire up to there. This one will wire up to there. But what we're going to do about the ground, because there's no local ground here, well, the answer to that is quite simple. It's a wire to the ground plane on the bottom. So there we are. Now we've replaced that with a surface mount transistor. And just to show you in 3D, it's a lot smaller. And the same go for resistors. And you could get this PCB into easily half the size if you use surface mount components versus using through-hole components.
Lovely.
So hopefully that explains that.
Yeah, we've got a few. I know it's quite late as we normally go on, but you're watching Tonight at 8 from the RSGB, and if you're happy to stay there a little longer, Mike, we've got some questions coming in now. So over to your questions. Andy, G0MJW says a brief mention of DRC would benefit viewers as it's probably the most useful feature of PCB computer-aided design. So can you touch on that? So does DRC is
design rules check. Yeah. Okay, well, you could do that in the schematic or in the PCB, actually, and it's this thing here. If I click on that, it will come up with all the errors in the PCB I've just designed, which you'll be pleased to see is none.
So DRC stands for Design Rule Check, and as Mike said, if you were to use this program, which hopefully some of you are going to go away and try, and you're not sure, say, if you've got, I don't know, a track maybe crossing another track or something like that, that would spot that?
Well, let's just put a random track there on the PCB who's not doing anything. Now run the design rules checker. Again. Warning. Track has unconnected end. And it's pointed out this track's got an unconnected end.
So that might be if you were working on something and then you went away for a break or came in another day and you forgot to connect the other end of it, that would warn you.
Yeah, exactly. And another thing you might do, for example, is let's take this resistor and move it a bit so that it's just overlapping that one.
Oh, right, yes.
So I'm just going to fill in the ground plane again. Now that's probably a perfectly valid PCB, but you can see that if we run DRC again, error. Courtyards overlap. It's also spotted that this track is no longer in the right place. And it's also spotted that lines on the silk screen are overlapping. So it's come up with a lot of errors because of that particular move. And you can either fix them or turn off the warning. And again, I'm just going to do a Control-Z to go back to what it was before, so that we don't have that, and then I'll run the design rules checker again. And all is fine. Now, in the schematic, it's going to be different again. So, and this, let me just zoom that. If I run the design rules checker on here, it's going to come up with quite a few errors. It's electrical rule check. It's come up with lots of simulation errors because I've not set up any of the simulation. So I can look at this and I can right click and I can say ignore all SPICE model violations because I'm not using a SPICE model. and it comes up with one thing, which is input power pin is not driven by any output power pins.
Unfortunately, as you said, we haven't got the time, and it's well beyond the scope of this particular demonstration to look at these simulations. But as I'm sure many of you at home will know, there are programs which can simulate what this circuit would do. So in this case, maybe a high power switch, and you can actually simulate it on a computer without running it to see if it would work, because sometimes you might be just designing something. In the old days, we'd have prototyped it and see if it worked, but this allows you to do that. Is that a fair summary, Mike?
It is, but you could do a bit more than that, because you can't just see if it works, you can see how well it works, so how quickly it'll switch, depending on certain parameters. And you can, the trigger voltage of the transistor, and you can look for instability. So if you took this switch and you, instead of the control pin going, say, 0 to 5 volts or something like that, it went to 2 volts or 2.1 volts with a bit of noise on it, you could then understand what that would do to the output signal, which might be very useful. And it might mean that you think, okay, this simple circuit's not good enough, we need to put a comparator or a Schmidt trigger in there or something like that.
Wow, very good. Peter M0OFM says, following on from an earlier question, if you had a junk box full of resistors, for example, with no data sheets, how do you calculate footprints? Could you show us maybe creating a quick resistor footprint, for example?
Well, what you would normally do is you'd find the closest and use that.
Okay.
But yeah, so there is a footprint editor. So if we go, let me just find the right bit again. So schematic editor, symbol editor. So symbol editor edits the symbols that you have on the schematic. PCB editor, footprint editor, edits the footprints. So if we click on that.
So maybe you're suggesting the best way might be to take an existing one that's close to it, or maybe the same, and just use that?
Exactly, yeah. Let's find well, I could find a complicated one, or I could find a simple one. Right, a resistor. So this is the resistor that's standard, but your resistor's different. And the difference might be the spacing, or it might be that things are offset. So what you could do is you can move the pads around. Let's say you've got a resistor that happens to look like that for some weird reason. So now you've edited that footprint so that when you come to put that on a PCB, that's what you'll get on the PCB. And if you want to, you can then also modify the silk screen, say, so that it makes it clear what's going on. So do you get the idea? You can change the size of things. You can make the courtyard bigger or smaller. So you can move these different lines around. You can expand things. You can change things as you see fit, really.
And then you can save it as a custom footprint.
Yes. Yeah, and then you can put it in your board. But more than that, actually, and I'm going to discard the changes because I don't want to wreck my resistor. But what I could do, for example, is I could look at one of these other components and I could modify that one. And I could, let's look at this pin, for example. I can edit the PCB symbol itself. Let's say, actually, I don't want a 1.3 millimeter pin, but I want a pin with a hole that's, say, 2 millimeters in diameter. And I want a pad that's 3.5 millimeters in diameter. And I can edit those things on the PCB, and as you can see, then it's got bigger, which might be, in a high current design, is what you want to do. Now you can then save that as a component, or you can just leave it on that PCB. And as long as you don't change that part, it'll stay there. Lovely.
Thank you. One other question I'm going to carry now before we let you have a well-earned break. And this is from Stuart Baker, who says, what changes can be made to the PCB, e.g. to the rat's nest, which is the name we kind of give, isn't it, to all the strings and what bits of virtual wires, and are they reflected back into the circuit capture? So can you change it on the circuit board, and does that then make the change back into the circuit diagram, I'm guessing he means?
Yes. So let's just make that a bit smaller. And let's make that a bit smaller and put it on the other side. And I'm going to highlight J2. And I'm going to edit J2 and make it J3. And I'm going to highlight J3. I can select it and make it J2. Sort of thing you might want to do.
So you've just swapped them over, really, yeah.
Whatever reason, yeah. And then here, oh, I'm being frustrated by Zoom. I should be able to, where's it gone? I should be able to update that from that. Update schematic from PCB. And see it's changing J2 to J3. And as I go in there now, that's now J2. The other thing that happens is if you select a component in the on the PCB, it will highlight it on the schematic. And similarly, if you select a component in the schematic, it'll highlight it in the PCB and it'll zoom in on it. So if I wanted to see, for example, where R1, which has disappeared off the screen, is, or R2 actually, then it will highlight that. So there are lots of things you can do. And one particular thing, and the reason, incidentally, that the numbering of all these components is so fortuitous, R1, R2, R3 and R4 aligned, is because when I did the design, first of all, what I did was one of the tools is to geographically reannotate, which is very useful because what you can do is you can, let's do it in a different way. Okay, that didn't do it in a different way because they're all still aligned. Let's do it that way. No, it's not. Sorry, I'm doing things wrong here. I don't want selection, I want all. There we go. So R1, R2, R3 and R4 are now the other way around. But of course when you do that you've got to be careful and you've got to update the schematic from the PCB. Whereas you see it's changed it now. Yeah, we saw the schematic change then. Yeah. As well. Yeah. And the use of that is when you come to build the PCB, it's very likely that all the components won't be in the same place they are in the schematic, especially with a complex thing. And rather than hunting all over the PCB to find out where R1 is and R2 is, if you rename them that way, then it's a lot easier to find them when you come to build the circuit. Indeed. Mike, what can I say? I think to take on something like this, you did it for the British Amateur TV Club last year at the convention, and we thought it would be lovely for RSGB audience, and you've done it live again, which is quite brave for a couple of hours of live designing a circuit board, but I think you've told me and you've told lots of people watching, gave them a really useful insight into this wonderful tool called KiCAD, which is free, so do download it and have a go with it. Once again, Mike, thank you very much indeed for this evening, and thanks to you at home as well for all the questions. Yeah, thank you, David, and hope the audience found it useful. I know from all the comments I can see they have. Thanks a lot. Thank you, and that does conclude this webinar, and thanks once again to Mike Willis, G0MJW, and also to the team who helped put this series together behind the scenes. We hope you've enjoyed this tonight at 8 and that you'll be able to join us next time. We'll be looking at how amateur radio can be accessible for everyone, even if you have sight, hearing or mobility issues. We'll be hearing from some people who've adapted their equipment, written software or taken advantage of extra support to take their licence exams to enable them to enjoy all that amateur radio has to offer.
Look out for more details over the next couple of weeks on the RSGB website at rsgb.org/webinars. And if you'd like to see details of future webinars or watch recordings of previous programmes in the series, please also visit us again at rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But until next time, this is David G0MJW signing off and clear. Bye-bye.